Hello, it's Keith here, and this is lesson 3 of my x86 assembly programming tutorials. Now, we looked last week at the addressing modes and we've looked at some basic mathematics in the past. Now we're going to start looking at loops and conditions and how we can do jumps and things like this. Of course, in the past we've looked at how we can actually get data into registers and move the data around. But if we're going to make any kind of program, we've got to actually make changes to what's happening depending on the contents of those registers. And that's where conditions come in. In addition to sort of conditions and branching based on those conditions, we also have some loop commands, so we're going to have a look at those at the same time because they're quite important and it feels like a good time to fit them in. And of course all of this comes into the concept of flags. Now, flags on the x86 are a set of bits within a special register, and these will be set based on previous mathematical conditions, and the effect of the branch commands we use will vary depending on the status of those flags. Now, we're going to do a variety of different mathematical operations that will affect each flag, and we'll see how the branches occur. So we will go into the flags in detail when we actually see the branch commands. So for now you don't need to worry about it. We're not going to do an initial summary of those flags because we're going to see them in practice later on. Anyway, let's go over to our code today and actually see them in action. Okay, so this is the lesson 3 assembly file, and the first thing we're going to be doing is a simple loop test. So let's have a look at this. Now, on the x86 we have a loop command. Now, if you remember, the x86 has 4 primary registers: AX, BX, CX and DX. These are of course 16-bit registers, and the CX is effectively the loop count. So that's what we're going to be using today. Now, the loop command will repeat, jumping back to a label, this label loop again here, until CX reaches 0. And you can see here, we've got this loop command here with the label specified. We're loading CX with an initial value of 5, and we're decreasing AX at the same time, and AX is starting from 10. You can see we've set it with this move command here. Now, we've got this monitor function here, which is going to show the flags and CX and AX. We're not going to go into how that function works. It's too complex for today. It's just a little program that I've written that's included in the sources 7-zip. So if you download it, you'll get that as well. So you'll be able to run this and just see the effect of that loop today. Now, you will notice, as well as this loop command, we have a jcxz command, which will jump if CX is 0. Now, before we just discuss that, let's see the routine in action here. Let's just run this. Okay, so here is our program has executed just fine, and if I just force that to be always on top. Okay, so you can see here that initially when we started, CX was equal to 5, AX was equal to 10, and then we decreased A and showed the result of all of the registers and the flags. So you can see here CX was 5, AX was 9 because of that initial decrement here, and then immediately after showing this we will loop again. So that was the first one. The second one, CX is 4, then it's 3, then it's 2, and then it's 1. Now, at the point that CX is 0, the loop back will not occur, and so we've printed this new line here, and then we've shown the final state of all the registers. So CX was 0 when the loop abandoned, and AX was still equal to 5 because there was no additional decrement because the loop had ended. So that's the status of CX and AX, and that's how CX and this loop command are allowing us to do a very simple loop here for a fixed number of iterations. Now you can see this jcxz command, which is a bit of a mouthful. Well, what's that do? Well, a common problem with your sort of loops like this, for example, if you created a routine that was going to show a set of characters depending on the count, if the count is 0, you would want it to print 0 characters, but it's not going to do that, is it? What's actually going to happen is the loop in this instance would run, get to the bottom, decrease CX, which would effectively become 65,000, and would then repeat showing 65,000 characters. So what you actually want to do is you want to check if CX is 0 before you do your loop. Now, I've put here a check at the start here, but I could actually put it just above here. But what this means is if I just stop this here, of course, if we change this to 1 and just run again, where you can see we've got no problem there because we've only run one time. And if we set to 0 here, oh, I've pressed my insert key there, that's not right, and I run again, well, you can see that's worked entirely correctly. We've shown no iterations before the new line and the final result. Now, what happens if I take out this jcxz command here? absolute anarchy, and that's 65,000 versions of the decrement command occurring there, or possibly even just corrupting the machine. Who knows what's happening? So as I say, definitely not what was supposed to happen, and that's because the loop has occurred too many times. But we didn't need that to actually be there. We could have just put it here, and that would have solved the problem. That's just fine. So that's what the loop and the jcxz command do. So jump if cx is not 0, and loop until cx is 0. Two very nice little commands there. Now there is another more powerful loop command which may be useful to you, and that is the loop nz command. Now if you think about it, before we were looping until cx became 0, so we were sort of already looping while cx was non-zero. So you might think, well, what does that non-zero refer to? Well, of course this refers to the flags. Now it's not referring to cx reaching 0, because actually when the loop command reduces cx, it doesn't actually alter the flags within the processor. It's actually referring to another command, and in the example I've done here, we're decrementing ax, and when that decrement ax command causes ax to reach 0, the 0 flag, the z flag, will be set. And that means that this command will continue, this loop nz will continue until either cx reaches 0 or the previous command causes the z flag to be set, in this case ax reaching 0. So let's just run that now and let's see it in action. Okay, well you can see it's that cx has started at 10 here and gone down until it's reached 3, finally ending at 2, but ax reached 0 first. So you can see in this case the 0 flag, you can see the z, that's the 0 flag in this monitor dump here. The 0 flag was set by ax, and that caused the loop to end, which is why you've got this new line in the final result. Now if I change ax to 18 and run again, you can see this time the 0 flag was never set, there's no z in here, and it was cx reaching 0 that terminated the loop here. So it gives us a kind of maximum value with the cx count, and also another parameter, in this case the decrement of ax, but this could be a compare statement. Don't worry if you don't know what that is. I know you don't. We're going to look at it in a moment, so don't worry about that. But it can be anything, and anything that sets the 0 flag would cause the loop to end in this example. And as well as non-zero, we have an alternate version, which is loop if 0. Now in this case that wouldn't make any sense, because that would only run while the decrementing of ax was 0, which wouldn't make sense. But for compares, if you were comparing two registers to each other, then if they are different, it would be non-zero, and if they're the same, the difference is 0. So again, that would be another case you might want to use these kind of commands. But this is just a very simple example of these in action. So you can see that 0 and non-zero, they are very important, and as I say, they don't just relate to a register becoming 0. A comparison operation is effectively looking at the difference, and if the difference is 0, the 0 flag will also be set. Let's have a look at that right now. Okay, so you can see here we're going to be doing some testing, and we've got a various set of options that we can do here, and we're going to be doing things to ax, and the end result, we've got these jumps. We're going to jump if 0, and we're going to show a z. We're going to jump if non-zero, and we're going to show an n, then a z. And if none of the above actually occurring, which in this example, of course, one definitely will, because the z flag is either set or it isn't, we're going to show, I think it's a dot it shows, but as I say, it's impossible for it to show that in this case. It's just there for completeness, in case you'd remmed out one of the other lines. Now, the idea of this example, of all these examples we're going to see from now on, is that you download them yourself and have a play around and try different settings going in, try enabling and disabling different options here, and see how things work, because I'm going to do my best to explain them to you, but I think some of them are going to be a little bit confusing, and maybe you'll be wanting to confirm if you've got it in your head right, and it's really good for you to try these out yourself. So as I say, any mathematical operation will change the flags, and we can see the flags with this command here. It will show the flags for us, and then we've got these jump, that's what the J stands for, and in this case JZ stands for jump if 0, and that will jump to the label specified here, and JNZ will stand for jump if not 0, if the 0 flag isn't set, and that will jump to this one here, and we're using with the print char, which again is something that's too complex for today. We're using that to show a character to the screen, so we're showing an NZ or a Z here. Now in the first example, we're loading AX with a 1 here, and we're decreasing AX, so it's going to become 0. So let's try that out, and let's just confirm that that does happen as we expect. Okay, so AX was loaded here. We then did the decrement. We've shown AX. AX is 0 here. You can see the Z flag here. And so there is a Z shown to the screen because we've effectively jumped here, down to here, and shown that Z here. Now, what happens if I run this line out? Well, let's try it. Now, what's happened is we've done our decrement. The 0 flag has been set. This line would jump if non-zero, so that didn't happen because it's not. And then this line is just the generic jump every time, and it showed a full stop to the screen. Okay, so you can see here we can use these various options. Now, what happens if I change AX to starting value 2? Well, our decrement will of course still occur, but this time AX equals 1, so that 0 flag's gone. The jump if not 0 has indeed jumped, and so you can see we've effectively shown an NZ here. So you can see that decrement commands will of course reduce a value, and if the value finally reaches 0, then we're going to set that 0 flag. So you can see that's that's very straightforward and very logical from a mathematical point of view. Now, what might be slightly more surprising is that the compare command, as I said, also sets the 0 flag. Now, what happens if we compare AX to the value 1 while AX equals 1? Well, let's just try it and see now. Well, you can see the 0 flag has been set, and we have jumped to the routine that showed the Z on screen. The reason for this is that a compare command, you want to think of it from the point of view of it's looking at the difference. Is the difference between AX and 1 0 or not? And the reason for this is a compare command actually updates the flags like a subtract command. But as I say, it's easiest for a beginner, I think, if you think of it as asking what's the difference between these two. Is the difference 0? Because if it is, then we're going to be jumping with this jump Z, and if it's not, we're going to jump if not 0. So that's how we can compare the values of things to fixed values. And of course, if we compared to 2 here, well, AX equals 1, we're comparing to 2, no 0 flag, and NZ is set here. You'll notice there's some other flags set as well, but we're going to go into those in just a moment, so don't worry about those. We'll get to them in good time. Now, as well as subtracting a value and it reaching 0, we can also end up with a 0 from an addition operation. In this case, we're loading AX with 4 Fs here, which is the absolute maximum value a 16-bit number can contain. Now, if we do an increment of that value, you're actually going to find we're still going to set that 0 flag. We'll just run it now. Well, you can see AX has reached 0 and the 0 flag has indeed set. Now, it would actually be clearer if I'll just add an extra one of these in here just to make it clearer. So you can see here that at this point, all Fs, no 0 flag, increased to 1, reached 0, 0 flag was set. It's a bit strange, isn't it? So this is a kind of quirk of these 16-bit processors. You may already know this. I'm kind of teaching this from an absolute beginner point of view, but I've covered it many times in my other tutorials. If you add a very high number to another number, you actually cause the processors to wrap around, and you can end up with a lower number than you expected. And in the same way, if we increment a very high number that goes over the limit of a register, it reaches 0. So that's why we've got a 0 flag here. But it's also quite important at this point to show you something else that we are going to have to understand. Now, what about negative numbers? These registers, a 16-bit register can store value from 0 to 65535. But we need to store negative numbers sometimes, don't we? We're going to need to subtract things all the time. So if I put a -1 in here and we see the contents of this register, if you're not familiar with assembly before, you might see something that will surprise you. Now you can see here that the -1 and the +65535 actually contain the same value. And it's to do with that wrapping around effect that I just described. And this is where you're going to really want to try this out for yourself, because you're going to think I'm talking crazy talk or something. But I've covered all of this in a dedicated tutorial on my YouTube channel. There was one where I went over in great detail assembly in hexadecimal. It was an 8-bit tutorial, but it's all totally the same on these 16-bit machines. So please check that out. But basically, if we've got a value of, say, 10, and we add 65535, well, that pushes us all over the way over the top limit of the register, back down to the bottom, and we will continue to just 1 before where we started. So 65535 is effectively the same functional value as -1, and it's just the commands we use and the way we treat the values that define if it's a very high positive number or a small negative number. If we've got a positive number and we want to, in our own heads, convert it to negative, what we can do is, if you take the bits of the value and flip them all and then add 1, that will convert it. But if we just want to use it in our code, the assembler does all the work for us here, so we don't need to worry about that. And we've got some of the commands to do things a bit easier to work out negative numbers for us, but that's the pseudocode, if you will, of how to actually make a negative number. So it's important I kind of explain these things right now. But again, if you think of your negative number of -1 and you add 1 to -1, you will definitely reach 0. And that's why 65535 FFFF in hexadecimal and -1 are effectively the same thing. So I know it's very confusing, but as I say, that's just the way assembly works with regards to negative numbers. So we've covered the basics of the equals and not equals flags there. Now let's have a look at signed numbers. As I say, effectively a signed number is if we can treat it as a signed number, a very high normal number, if that makes sense. And as I say, effectively, if you want to take a value like 1 and convert it to -1 in hexadecimal, you flip all of the bits and then you add 1 to it. So 1 converted to a negative hexadecimal number would be FFFF. Now, you probably can't sort of figure that out in your head, but this effectively means that the top bit of a register will denote a signed or unsigned number if we're treating it as a signed number. A signed number would go from -32768 to +356767, or an unsigned number would be 0 to 65535 in 16-bit. So the top bit, if the top bit is a 0 and it's a signed number, then that's a positive number. If it's a 1, then it's effectively a negative number. And we have some commands to branch if that top bit is effectively 1. And as I say, this comes into a bit quirky stuff, because if we're treating it as a signed number, then this is how they will work. But we can also use this to just check the top bit quickly if we want to branch based on a top bit, like if we're reading in values from byte data and we just need to see if the top bit is a 1 very quickly. Sometimes you would do that on some processors. Okay, so let's fire this up and let's see it in action. Okay, so in our first example, we've loaded AX with a 0 here, and we've added 1. So of course AX equals just 1, very simple. And then we've decided to branch depending on if this is signed or not. Now the top byte here is a 0 here, so the top bit is also 0, obviously speaking. And so according to the branching of signed or not signed, JS and JNS, then this isn't a signed number. So we've shown an NS to the screen just because we've jumped to here, shown an N and then an S. So you can see here that that is an unsigned number, as I say, effectively because the top bit is 0. Now, if we do a decrement here instead of 0, then of course we're going to go negative. And you can see here, once again, that's FFFF. And the F symbol here is effectively 1111 in binary. The top bit of that is, of course, a 1, so it's a signed number. The S flag has been set. And we've branched and we've shown an S here. So as I say, you can see that that's how it's working. And of course, this is how we would need to work if we were, maybe we've got a piece of code that was moving a ship up and down, and we needed to show the sprite differently if the ship was moving up, going up the screen, and that was a negative number. So as I say, there would be definitely times you're going to need to do this kind of thing. And so this allows us to quickly check if a register is positive or negative at this point. Now, of course, it's entirely true to say that this works in a wide variety of ways. So let's just put a much more large number in here. Let's do 32767. As I say, the limit of a negative number in signed arithmetic on 16-bit is -32768. Now, 32767 would be effectively 8001. Now, the top nibble of 8 is 1000. So this is the absolute smallest signed negative number we can have. So you can see the sign bit is still set, and you can see that S there. However, if we add in another decrement here and run again, well, now that top bit is a 0. 7 is effectively 0111 in binary, and so we've now lost our sign bit, and so this is said to be a positive number here. So we're no longer a negative number here. And as I say, that's I know that's going to sound confusing to you, and if you don't understand it, as I say, you probably don't need to worry about it just yet. I'd suggest you have a look at that other tutorial I've done on signed numbers before on hexadecimal mathematics. But you can carry on with this tutorial and the further tutorials. I think signed numbers are going to be a thing you're going to be a bit confused about at the start. I certainly was. You'll get more understanding with them as your need to use them becomes greater, and what I'd suggest is, as I said before, download these tutorials, have a play with some sample examples, showing them to screen with the monitors, and see what kind of values are coming out when you're specifying values in here, doing addition, subtractions, seeing the status of the flags and how these jump if signed and if not signed are working. That's how I figured them out. I think that's going to be the best way for you too, because in a certain way, no matter how much I talk about them, there's going to be things you're going to need to think through at your own pace, and seeing the numbers you're thinking of and you want to see how they actually affect the flags and things work in your own time. So I'd suggest you definitely get the source code and try these out. That's the reason I make the source code available. So that's how we can test the sign itself. Let's actually try out some branches based on unsigned numbers and testing if they're higher and lower, because as I said before, a register containing FFFF could be considered to be 65535, or it could be considered to be -1, and both are entirely true. It just depends on how our code is working. If it's a score on a pinball machine, it's not going to be negative, but if it's a bank balance and we're doing it very badly that day, it definitely could be a negative number, although you certainly wouldn't use a register for your bank balance, because if you did, you might accidentally roll it around and become a millionaire one day. So don't do that if you're writing 16-bit accounting packages. It's just an example. Anyway, you can see here, we're going to try it again. We're loading AL and BL. We're going to compare these two together, and this time we're working at 8-bit. You can see I'm only showing these on AX, and I'm showing them with some very limited values, but these got a wide range of addressing mode options, and as I say, you can use 8-bit and 16-bit, and that's why you need to try this out yourself, because 8086 isn't like Z80. You can't print out every permutation and combination on a single sheet of A4. It's a much more powerful processor. So we're loading AL with 10 here, we're loading BL with 5 here, and we're comparing AL to BL, and this is going to effectively, I've made a mistake here, this should be AL here. So we're going to compare the A value to the B value here, and we're going to jump accordingly. So if there's no jump, we're going to jump to this dot. If there is a jump, we're going to jump and show this J. So first we're going to check if A is above the value in B. So we would expect it to be. So let's fire this up. And you can see we have indeed had a jump. So A was greater than 5, because it's 10. AL was greater than 5. And so we've jumped. Now, if I change this, and I change this to 15, which you can see was actually down there just below. Well, guess what? A is now lower, so we haven't jumped. We've jumped to this no jump here. Of course, alternatively, we could change this, and rather than using jump above here, we could use jump below. And you can see that because A was below B, we have now jumped again. So we got options to jump if above and jump if below. We also have options to jump if above or even greater than equal effectively. So if I just set both of them to 10 here, well, you can see we've now jumped, and that's because the Z flag had been set because it was equal here. So we've got a wide variety of options here: jump above or equal, jump below or equal. And the important thing to remember is these are unsigned comparisons. Now, if we compare to, let's just change this for a second. We'll change this to AX and BX here. And if I compare AX to BX, my typing is terrible. So we're going to see if A is above BX here. And I'm going to change this to 65535, which is an important number. And you might remember it. So we have jumped here because 65535 is blatantly above 10. So we've jumped down here and shown a J rather than not jumping and showing a full stop. Why did I choose that number? Well, maybe you remember that number. Let's change it to -1. Now, any fool would understand that -1 is below BX here. So A is below BX here. So we would expect not to jump here. But while any fool may understand it, in this case the processor has not. The processor thinks -1 is greater than 10. And the reason for that is this is unsigned logic. This is treating the values as being 0 to 65535. And a signed number of -1 is the same value as 65535. We have to use different commands for signed and unsigned mathematics. And if we don't, we're going to get weird effects like this. So as I say, when I started learning Z80, I was convinced there must be some way of telling the processor that this is a signed register, this is an unsigned register, but there isn't. The commands you use are different and the way you treat the numbers are different. Signed mathematics, I always think of it as kind of like a quirk of the processor because, as I say, it wraps around the values when it gets to its upper limit. And it's that wrapping around that causes you to end up at a lower value than you started. It's kind of like an addition. That's the way I think of it anyway. So those are the commands for unsigned numbers, and they work very nicely. But as I said, if we're using signed numbers, they're not going to work very well for us. So we've got some other commands to do that. Let's get those up right now. Okay, so here we've got some more. Now this time we're loading AL with 10, we're loading BL with -15, and we're going to jump if A is greater than B. Now A is 10 and B is -15, so this should work quite nicely, you would think. Let's check it out. So we've jumped if greater than or equals. A is greater than or equals to B, so it has jumped. Okay, so let's try another one then. So that's had a nice jump there. Now if we do less than or equals, you see we've got G, jump if greater, JGE, jump if greater than or equals, JL, jump if less, JLE, jump if less than or equals, and all of these are doing signed mathematics, because again that's important because of those very high numbers or effectively negative numbers. So if we jump if less here, well, you can see now no jump occurred. You see we've just got our full stop because A is 10 and B is -15 here. But if we now change A to -100, well, A is now less than B, so once again we have jumped. The important one, in the same way as before, if we change this to 65535 and we change B to 32, well, we will get some very silly results because those are 8-bit registers and I've just put a 16-bit value in. So getting back on track and remembering what bit depth I'm working at, we're storing 65535 in AX here. We're loading BX with 32, comparing AX to BX, and we're going to jump if AX is less than BX. Now, again, 65535 is definitely bigger than 32, but if we run, well, it shouldn't be a surprise at this point. It might be. As I say, I understand you. I'm giving it this pretty fast, but if you're understanding the way that the negatives are working, negative 655 is the same as -1, and -1 is lower than 32. So again, we've used the wrong command here. If we wanted to compare an unsigned 65535 to a 32 here, rather than JL, we wanted to use JB because JB is the unsigned jump if beneath, whereas JL is the signed jump if lower. And so this time, AX is 65535 is not beneath 32, so we have not jumped, and we've shown the dot because of the no jump. So you can see there that we've really got to be very careful when we're using these commands, these jump commands, and we make sure we are actually branching depending on the correct set of settings. Now these branches, depending on greater than or less than, are actually using in some cases a combination of flags, and at this point I don't think it's really necessary for you to know which flags are being used because it does get very, very complicated, and it's just going to confuse you. The important thing is you use the right command depending on the jump that you want to perform based on the registers that you're looking at. Now, in addition to these ones that compare if greater than or less than and things, we do have some rather unusual ones. Now, the first of these is the parity flag. This I've never used. I've got to be honest, I've never knowingly used it. What this does is it will compare all of the bits in a single byte, and the flag will be set to 0 if there's an odd number of 1 bits, or 1 if there's an even number of 1 bits. Now, you may be familiar with the parity flags if you've sort of done things with barcode readers or and if you've done any sort of programming with regards to reading in data and double checking that it's been entered correctly, you may be familiar with checksums and parity and things. And so I can imagine why you would want to use this kind of thing and why it might be useful. It's just for me personally, game programming. It's not been something I've had to do myself, although obviously cassette reading routines may have had it built in and working in the background without me worrying about it. But as I say, we're going to cover it just now and we're going to look at it here. So we're loading in AX with a value here, and we're loading in just a bit 1 here, and then we're inking it, which will effectively set bit 0 here. And we're going to show PO for parity if odd and PE if the parity is even. And you can see we've got 2 jumps here. Let's just fire this up and see what happens. Okay, well, there were 2 1s, so the parity has been set to even, and you can see the P flag has been set. And you can see actually the 2 1s just here. Now, what about if I change this command? Well, if I add an extra ink, well, now a 2 is effectively 1 0 in binary. So again, there are 2 1s, so the parity is still actually even. Well, what about if I do another ink? Well, you can see here I've actually marked the binary just on the source code here. It's now 1 0 0 1 1. Well, the parity is now odd. The parity flag is cleared here. So you can see because there are now 3 1s in the resulting value, the parity flag has cleared. But if I set another ink, well, now we've effectively got 1010. The parity is even because there's 2 1 bits, so the parity flag has been set there. As I say, I think there's going to be cases where this is going to be really handy for you if you're trying to do reading in and checksums. I've never needed it. If you can think of a great reason why this is a essential game programmer's tool, let me know. I'd love to hear it, but I can't initially think of a case where this is something I've needed to do in the Z80 and things. It's just never come up for me. So as I say, I'd be interested to hear what you think I should be using this for, and I will, if you can think of it, I will endeavour to use it for that purpose. But that's what the parity does. Now, the final one we're going to cover today is indeed more useful. Again, it might be not something you particularly need, but you definitely need to know about it. Now, inside mathematics, a very low number like minus 32768 is right next to the very high number 32767, because as I say, they're effectively they're on the same sort of scale. So if we've got a value that is very low negative number and we subtract a very large number from it, the result is actually going to end up positive, which sounds crazy, I know, but think about it. As I said before, if you think of like minus 1 is 65535 and plus 1 is just 1, well, some point along there they're going to cross over. So if you've got a number here that's negative and you suddenly subtract 32768 from it, you're going to jump all the way back to here and your sign is going to flip, and that's going to be a serious problem for you. Like I said with the bank balance, if your bank balance is going down and down and down and down and you're using a 16-bit number for your bank balances, and all of a sudden you go below minus 32768, you're going to end up at plus 32767, which for the bank account holder is going to be a very good day, but for the bank it's going to be a very bad one. Again, just an example. I know you wouldn't use those kind of registers for that kind of value, as I say, just an example. But as I say, we're going to need to be able to check if our mathematics is causing the sign to flip. So that's what the overflow does. It's when a register's value has gone from negative to positive, because that's going to be a serious problem. So in this case, we've got 32760. Now 32767 is the maximum positive number. Anything higher would effectively be a very low negative number. So we're adding 32 to this, and that's going to go badly. So let's try it. So you can see here that the top bit has now been set to 1. Remember, 8 is effectively 1000 in bits. So this is actually a negative number. It's a very large negative number. And the overflow bit has been set because we've overflowed the positive limit of AX here. Now, if I change this from a 32 that we were adding to just a 2, and I run again, well, you can see now that 7, that's 0111, so the top bit is still a 0, which is a positive number, which is what it should be. So we've not overflowed. So we've got an O here, because that's what our jump shows if we didn't overflow. You can also add 7 here. That will work just fine. Not overflowed, because again, but you can see we're right on the limit there. So if we add 8, well, you can probably guess we're going to overflow there because, again, that top bit is now set to 1, and we've now got a very, very small negative number, whereas before we had a very big positive number. So that's how we can use the overflow flag to keep our values in check and make sure that our mathematics isn't causing problems. I believe overflow is also used for division for the same kind of reasons, so we might see it again later on in a future tutorial. Now, of course, this isn't just relating to a problem with very high positive numbers in signed mathematics, it's also very low negative numbers. So if I do 32760 and I do sub 2, well, there's no overflow because we're still a negative number here. Top bit is still 1, so that's fine. But if I do sub 200, well, we've converted that into a positive number, and that's the example of this bank balance going below minus 32768 and ending up plus 32700 or something like that. So as I say, it's something we need to be aware of if we don't want our ship to fly off the bottom of the screen and appear back at the top and things like that. As I say, you have to be a bit careful with these mathematics when you're using these signed numbers sometimes. So there we go. Now that's actually all of the examples I wanted to cover today. It's a bit of a shorter lesson in some ways, especially compared to last time. I tried to split these lessons by topics, so some of them are very long, some of them are very short, some of them are a bit tough, and some are a little bit easier, but I think it's better than jumping around and giving people little bites of information that don't quite fit together, and if people get confused, they don't know where to go back and look and relearn things because they can't remember where the discussion of the overflow flag was. And so, as I say, I cover everything in one go because I think that's the best way of making them easy to understand. So I hope you've found this interesting. I hope you've understood it. As I say, I know some of it's a bit tough and a bit daunting and you may not understand it yet, like negative numbers. Don't worry about it. Just carry on with the rest of the series because each episode, while it will build on the last one, doesn't necessarily require you to have understood everything from the previous lesson. As I say, some of the stuff here I've never used. The overflows I didn't need for Chibiakimas really, and the parity I didn't need that at all and never needed it. So as I say, you don't need to understand everything. As long as you've got the grips with the ability to compare higher and lower numbers, and the zero flag is the most important, I think you're going to be fine with the later lessons. So again, just bear this one in the mind for the future and come back to it later on when you've got new questions that you want answers to. Anyway, I hope you found this interesting. I hope you've enjoyed what you've seen here. As I say, please go ahead and download the source code, have a go with it yourself. I hope you enjoy programming and I hope you enjoy the 8086. Thanks for watching today and goodbye.